The broadcast is now starting. All attendees are in listen-only mode.
Hello and good afternoon, everyone. My name is Anna Zylik. I am with ICF, and we are the vendor working on behalf of the sponsors of Energize Connecticut to bring these Passive House trainings to all of you. So thanks for joining us today. We will be recording this training, and we will make this available afterwards. These trainings are at no cost thanks to the sponsors of Energize Connecticut and are part of a partnership with Connecticut Passive House. A reminder that as part of this training and workforce development initiative, we are offering a 50% cost reimbursement for individuals pursuing either FIAS or fee professional accreditation. So this includes the cost of the training and the exam, and once you become certified, we'll work with you to process the 50% cost reimbursement. So if you have any questions on the reimbursement process, please don't hesitate to contact us. With that, I'll pass it over to Jamie, who's also with ICF, to talk about the Passive House building incentives.
Thanks, Anna. Hello, everybody. Thanks for tuning in today. We're excited to have everybody here. In addition to the no-cost educational training series and the professional accreditation reimbursements, the sponsors of Energize Connecticut also offer robust incentives for builders and developers who choose to pursue Passive House certification in multifamily projects with 5 or more units. Can you go to the next slide? The Passive House incentive design for Energize Connecticut is shown on this slide here and includes pre-construction incentives for feasibility studies, energy modeling, and post-construction incentives for full Passive House certification. Our goal is for everyone involved in multifamily construction in the state of Connecticut to be aware of these incentives, so please help spread the word. For anyone interested in learning more, please visit our website or contact us directly at the address on this slide. As far as for questions during today's session, Anna and I are going to be monitoring the Q&A box, so we'll relay them over to Scott when your questions come in. So with that, I'll turn it over to today's presenter, Scott Pusey from Stephen Winter Associates. Thank you so much for being here, Scott. Take it away.
Thanks, Jamie. Thanks, Anna. Hi, everybody. Welcome to Workshop 3, Part 2. This is the last of the series. And so we've got, similar to other talks, we're going to follow our same sort of outline, but this time talking about ventilation systems, specifically central and individual systems, and considering those different 2 typologies when trying to design and then install them. And then after the break, we're going to talk about testing and adjusting and balancing. So some other things that are a little more field specific, kind of during and after construction. As with all of our presentations, we're wondering if you would be able to tell us who you are. Who is listening today? Looks like we've got about 20-ish folks on the call today. In the past, we've had a lot of contractors, always a consultant or 2, and some architects. Wondering if that is similar to today's audience. Yep, there we go. And the next slide is going to be trying to find out what you are hoping to learn today. And so no consultants today? Usually have 1 or 2. All right, so we'll definitely talk about design. We're going to talk about installation issues for both architects and contractors. Welcome, an owner developer. Great. Wait a minute, I think we had some more response. Cool, so mostly architects, a lot of design folks, and thanks for responding. Moving on to the next one, what's something that you're hoping to learn about? Last time during ventilation, we talked about sort of like ventilation at a high level. We talked about ASHRAE, which is kind of a standard that the industry uses. ICFA, okay. Well, we might not get that specific about ICFA. That is specific to Passive House and how they define the floor area. But yeah, sorry, we probably won't get to the nitty-gritty of that. That's more in sort of like a certified Passive House consultant's training. Cool. Balance systems, commissioning, design testing and commissioning. Great. We are going to talk about that in spades. So why are we here? We talk about this every time. Pushing for Passive House as a pathway to building electrification. As Jamie mentioned, there's incentives available, got a bunch of benefits for doing this. This is workshop number 3. Here are the goals of a high performance building stated again. We look at these slides every time, but it bears repeating. These are the Passive House pillars, sort of the pathways to get to high performance. So we're going to talk more about balanced mechanical ventilation today, obviously. This is what continuous insulation looks like. This is how we test air tightness. These are the very high level basics about ventilation and heat energy recovery. Fresh filtered air 24 hours a day for Passive House, good efficient heat exchanger, and highly insulated and air sealed ductwork. We're going to talk a lot about highly insulated and air sealed ductwork today. All right, let's jump right into it. So for Passive House, for high performance, usually an exhaust only approach is not going to cut it. So exhaust only, again, we talked about this last time, referring to using an exhaust system to provide the whole building or whole dwelling unit ventilation needs. So to sort of dilute those pollutants that are in everybody's homes. In a tight building, we need some of this mechanical ventilation. And so when you do it 24/7 using an exhaust approach, this is some of the stuff that you see as unintended consequences. You basically are dragging that outside air through your building enclosure, through the gaps, cracks, and holes that do exist in it. And this is an example of, call this filter glass in the industry, right? The fiberglass vats are sort of filtering that outdoor air as it moves through this building enclosure, which is not ideal, not really what we want to have happen. Balanced ventilation is what we're going to talk about today. Specifically, it's going to be pretty specific to the Passive House standard, but again, Passive House as a gateway to high performance is really what we're trying to emphasize with these talks. And we're going to talk about sort of 2 typologies, 2 kind of designs, a central system design and an individual system design. I know most of you on the call are here to get information about doing low-rise buildings, single-family homes, that sort of thing. This individual system is going to be sort of more relatable, I think, to that kind of design. But we wanted to include the stuff about central systems because we're here. We might as well. We have the information. We want to share it with you all. Speaking of more information, there is a very detailed blog post on our website talking about trying to decide between central systems and individual systems when it comes to ventilation. I'm going to talk about it a lot over the next couple of slides here, but if you wanted something as sort of a takeaway, you could also refer to our website, do a search for unitized versus centralized HRVs, ERVs. All right, so just a reminder about what balanced ventilation is in terms of Passive House requirements. So it needs to be balanced, and Passive House defines this balance as the supply and exhaust flow rates are within 10% of each other. One of the things that you want to do is to supply to all living spaces and exhausts from those kitchens and bathrooms. So this is a case where last time we talked about whole unit, dwelling unit ventilation, which we're going to talk about again today. We also talked about those spot ventilation requirements. In the passive house approach, we sort of combine those two things into one system. So not only is your ventilation system supplying fresh air to the living spaces, it is also exhausting from kitchens and bathrooms, usually through one box, usually through one piece of equipment. And it is an energy recovery ventilator or a heat recovery ventilator that is at least 75% efficient. This bullet point number 5 is referring to keeping the temperature of the outside air that's coming into the space, intentionally through the ERV, trying to keep that above 62 degrees Fahrenheit on the coldest day of the year, the coldest hour of the year. And so having that design capable of doing it, if it's in a cold climate or a very cold climate, usually this is going to involve some kind of duct heater, but you can also do it with very efficient ERVs or HRVs. So passive house recommendations, these things are not necessarily like mandated in the ventilation requirements per se, but they're probably going to have to be implemented into what you're doing in order to meet other requirements of the passive house standard. So one of those is number 2 on the second set of bullets here, the fan power efficiency, looking for something that is going to deliver an efficiency of 1 watt per CFM or less. So this is the electrical energy that the ventilator uses to move that air around, not necessarily the efficiency of the core, not the efficiency of the heat transfer mechanism. This is more how efficient are the motors to move the amount of air that is needed. Number 3, allow for a buffer in the energy model for additional fan energy due to duct leakage. So we're going to talk about this a lot. It's kind of one of the biggest kind of sticking points to getting passive house really working well, in the design, in the actual building. Spoiler alert, it basically means, you need very tight ductwork to move this ventilation air and distribute it around the dwelling unit or home. So this is sort of like the bottom line up front. Okay, so these are recommendations for a successful project design, and we're going to flush these out a bit more as we go through it. I wanted to put them right up at the top though, just to make sure that everybody is still paying attention when we get to them. So sizing the ERV is a big deal, and sizing it, our recommendation to our project teams is to allow some wiggle room in the design. So size the ERV so that the standard operating flow rate, kind of like what you're shooting for, what the design case is, give some more range in the box that you pick. We're saying here 50% of the maximum flow of the unit to optimize efficiency. So you don't want to have an ERV that is running full out, all out, just to meet the minimum design requirements. We're suggesting picking something that maybe's got a bit more capacity, that it can run sort of like, in the mid-range of its operating range. And this is going to allow for additional fan capacity to overcome any system leakage if it happens. So unlike heat pumps, we are advocating for a little bit of oversizing of the ERV, but you want to give controllability to the ERV, right? We want to be able to dial in the amount of airflow that we want with like a speed controller on the ERV. A lot of them that we talk about, that I'll talk about today in this passive house world, have the ability to ramp up and ramp down and be set using controls to what fan flow you want it to be. So take advantage of that on the market. Account for a buffer in the energy model. So again, for system leakage, you want to make sure that the certified passive house consultant, i.e. the person running the energy models, to see if the project is compliant or not compliant to passive house as modeled, has enough buffer room in the energy model to say that you can handle a little bit more fan flow, right? Like you could have more outdoor air being delivered to the spaces and taken out of the spaces than the minimum. So we'll talk about that, and I'll show you some slides on design rates, but we're saying to buffer into the energy model then that, a range, the higher end of, pushing more air into the enclosure. Because not allowing for leakage could cause failure to meet the space conditioning, like your energy model would fail if you have a lot of leakage in your ductwork, and that's causing you to increase the amount of air that you're pushing into the space. And then understanding that the energy penalty of additional system leakage on the energy model is also going to increase that fan energy in a watt per CFM increase. So taking that into account into the energy model, and then making sure that the ventilation ductwork and the heating and cooling system ductwork is not like difficult or impossible to construct. So constructability in the ventilation design. All right. We'll talk about individual systems first. So a couple different kinds of individual systems out there. This is a Zehnder product in the middle of the screen. This is a large ventilator, definitely more for a single family home, and probably a pretty good sized single family home at that. This is a manifold where all of these tubes are sort of like individually running to the spaces, to the rooms. So think of it as kind of like the PEX piping of ventilation systems with this kind of arrangement, right? Central manifold, individual runs. So these are both supplies and exhausts to those spaces. And then compare that to sort of a smaller unit that's got, I think this is probably a little more typical of what you would see on the US market, and what at least I've seen, on non-passive house projects. But, you've got your fresh air in, stale air out, and then fresh air being delivered to the spaces and exhaust air being exhausted from, kitchens, bathrooms, that sort of thing. So other things to consider when talking about individual systems. Got some slides to illustrate this as well. These are sort of what we're going to go through in the next couple of slides. The placement of the ERV, the access to it, how you duct and how you lay out that ducting. Is it going to conflict with anything, right? You have room to run the ductwork. Do you have the ability to get in there and seal ductwork? Sealing of exterior ERV ports. There's pressure balancing. Got to keep the exterior grills clean. And then there's also considerations about how we'll test and sort of commission this, not only for duct leakage and the flow rates of the ERV, but also the blower door testing. There's some interactions there. I'm going to turn my video off so we can focus on these screenshots. All right, so ERV placement, taking those bullets sort of one at a time. This one is in the middle, more of a closet. Well, it's right here. This is a little ERV closet. That's the only thing that's in this closet. You see it's right next to the exterior wall. So pros of this, you're limiting the amount of ductwork between the inside and the outside. You're also limiting the amount of ductwork that you need to insulate really well, right? Because we said during one of our previous talks that, sort of like contrasting it with this other way of doing it, having the ERV sort of, this is a corridor of a multifamily apartment building, but this RV is well into the living space. And so you have long pieces of ductwork to insulate because you know, this incoming outdoor air in the winter is going to be quite cold. You really got to do a great job insulating it. There's also heat loss associated with that, right? So this the length of the ductwork and the insulation, the R value that's on that ductwork, all goes into the energy model. These are all considerations that are handled in WUFI or PHPP, the two modeling protocols for passive house. And so the shorter the ductwork between exterior and the box, the better for the energy model. And it's a little, I think it's a little easier to implement on site as well. So this one in the closet, obviously it's in a closet. This one is actually located in a drop ceiling. It's above a drop ceiling. And we've got some photos of that. So are they accessible? Can you get to them? We'll see those in the next couple of slides. All right, so here's the ERV closet example. You can see it, you know, sort of roughed in, right? These ducts are going to go right to the outside, one high, one low. This is what, you know, the cover of that closet looks like. It's lockable, etc. Looks, you know, pretty inconspicuous. And then once you open that door, this is what it looks like inside. And you might notice it can be, it's a tight fit here. I think this door actually did swing open, right? Like this is the front panel of the actual ERV cabinet itself. Got to make sure that you can open it, because that is where those filters are to get in there and maintain them, i.e. clean them or replace them. This is what that individual, that ceiling mounted one looked like. And so you can see it's suspended. We've got our fire lid up above. There was drop ceiling that was put, you know, underneath here. And so this cabinet actually swings down. And so the concept here was just slide the panel of the drop ceiling out of the way, pull the panel down, and then you have access to, for your maintenance and cleaning the filters and everything. All right, so moving on to sort of the next consideration, ducting, layouts, conflicts. So here is an example of, you know, have the HVAC contractor probably having to, like, on the fly go around stuff in the, you know, around, this looks like a sprinkler, yeah, probably sprinkler, or, you know, domestic hot water pipe. And so we note it here, and we note it in our field inspections when we're looking at this stuff on site to say, hey, that looks like, you know, an unplanned jog, right? Usually in a lot of the engineering literature, you know, anytime you add a 90-degree elbow, it's like adding, you know, another 15 to 30 feet of straight duct run. So that's got real implications for how well these systems are going to distribute, you know, sort of what the flow rates are going to be at the end of these duct runs. And within Passive House, because the flow rates are so low to begin with, any little change could have a significant impact. And so what we're saying here with the slide is, when you do the design, you want to be conscious of what's going to get in the way so that you can limit or totally eliminate the amount of jogging around that you're going to have to do, because it could possibly have, you know, a negative impact, i.e. you don't get enough airflow out of the register because you added more elbows. So spaced for duct sealing. This is not the same thing as the adding more, you know, jogging around stuff. Like, you know, this duct was designed and meant to be pinned to the underside of the floor above. And so what happens is a lot of times, you know, you can only do so much sealing of this metal, round metal ductwork sort of on the floor before it needs to be put up to the ceiling and installed, you know, connected to the next piece, right? So an elbow is a great example of that. Usually, you know, this is not going to be put up as all one big piece of ductwork, right? And so if you can't seal the top of it in this case, because it's pinned and attached to the ceiling, you know, we can see this when we do inspections. You can see that there's mastic all over the ceiling, like all over the structure that's next to the ductwork. That's because, you know, it was mastic while it was in place. And so if you can't get in there to seal, it's going to leak, and it's going to be a problem because it's going to reduce the amount of CFM that's being delivered, you know, either delivered or exhausted to the actual space that it needs to be delivered or exhausted from. So the really good installers are going to run any long seams down towards the floor so that they can seal that long seam, right? Like these are the short seams that are happening as these pieces are getting fit together. But you also need to seal the long seams as well, if I could talk today. So allowing space to do the duct sealing is what we're talking about. Pressure balancing. So pressure balancing refers to having a bedroom that doesn't have a pressure difference across the closed bedroom door. And so pressure balancing is going to be accomplished usually by transfer ducts. In the case of single family homes, it could also be accomplished by both supplying and exhausting the same amount of ventilation air out of a given space. You know, usually that happens when there's a bathroom, you know, attached to the bedroom. But in kind of like, I don't know, a kid's bathroom or something, right? Like usually like a door undercut, but more likely a transfer grill is going to be needed to alleviate the pressure difference, because you know, you're supplying fresh air to this sleeping zone, to where the people are spending 8 hours a day of their time, you know, while they're home. You want to, FEIS requires that you provide fresh air to that space. And so if you're just pushing air in, you need to allow for a return path so that it can get back to wherever the exhaust port is. And this is what we mean by having it be pressure balanced. So providing a dedicated pathway for that air to get back to the ventilator, to get back through the exhaust ductwork. And that's just, you know, one example. The bedroom is usually where it happens the most often, where you're pushing air, supplying air there, but maybe not necessarily exhausting air out of the same room. You're exhausting air out of a hallway bathroom or something like that. Okay, so what are some other potential issues for these unitized systems? You saw the ERV closet. I don't know that this is the same. Yes, this is the same project. And this was the first iteration of the contractor installing these individual ERVs and having the ductwork and everything run. So a whole bunch of stuff here that is problematic, and I'll call them out as I go. So they're small, right? It's a small space. The amount of ductwork that needs to be in here, you know, this is the ventilator, here's the outside wall. And so you can see this is done, I think this is done in Flex. No, maybe it's not Flex. This connector here is definitely Flex ductwork. And for ERVs, Flex is a no-no. It's really, you really want to stick with the hard metal, you know, the least amount of friction. And because again, those flow rates are so low, the tolerances are so low, Flex ductwork doesn't do a great job. I mean, I guess if you have it in accounted for in your design, it might work, but you know, even here we're calling it out. It's just a, you know, a small transition piece from the actual ventilator to the run, and we don't want to see that. It certainly wasn't called for in the plans and specs. The HVAC contractor sort of snuck it in here. Other considerations: it's difficult to properly air seal and insulate these exterior wall connections because it is so tight. And so yeah, sort of the tight bend here, you know, if this is accounted for in sort of the duct calculation and how much airflow this thing is moving at such and such a static pressure, then, you know, it's probably okay. Is it insulated well enough? Yeah, it looks like it. I think what we're calling out here is that, you know, the R8 runs need to be at least, you know, they can't be any more than 5 feet. Like that's what we were expecting in the plans and from the drawings, right? So this run going all the way up here is a little long, is kind of what we're calling out. And then again, future maintenance and access to the apartments for filter changes. So, you know, being able to get in there and change the filter. All right, so here in the right side is sort of like an up close and personal view of it. And so there's a lot of transitioning going on here. Not only is these hard ducts kind of serving as a transition from the ventilator itself to what looks like more, I guess it is more flex duct. I guess all of this is flex. Oh, yeah. And so all these opportunities for leakage to happen, not only do they need to seal the actual hard duct, they also need to seal the transition into the unit, and all of this needs to be insulated. So kind of a pretty bad job done at installing that one. Other potential issues, not just for individual systems, also for central systems, is filter maintenance. This is an example of the interior, you know, the actual ERV vent, the actual ERV filter. It's filthy. These things need to be cleaned, you know, at least 3 times a year, some probably 4 times a year, once a quarter. This is an example of an outside port. We talked about needing to clean that off. You can see all of the, you know, dust, gunk, whatever from the outside air is getting all trapped in there. It needs to be cleaned so that it can be handled by the filter, and then the filter needs to be changed regularly. Okay, we talked about blower door testing prep. So on a multifamily building, when you do individual ERVs, you know, there's a lot of them, right? Like this building right here, it's only 3 stories. There were 60 apartments in this one. This is a picture of the HVAC installer, you know, prepping the building for blower door testing. We need to seal off these vents so that we're not picking up the ventilation flow rate. We're not counting that as infiltration that would be picked up during our blower door test. So another consideration for Passive House is how are we going to temporarily temporarily seal off all of these ports so that the ERV, you know, the ERV flow is not being counted as part of infiltration, because it's not. It's not infiltration, it's ventilation air. It's intentional air. All right, if there were any questions about sort of individual systems, now would be a good time, because we're going to talk more about central system considerations next. And you can see the central system just, you know, has a lot more ductwork, especially, you know, the addition of a riser to move air from lower floors all the way up to either the roof or, you know, the ground floor, whatever. And so while it's easier to access and maintain, the amount of ductwork that exists and the amount of the sophistication of the controllers that are needed to ventilate both common areas, residential areas, unoccupied areas, etc., can be a little complex, but definitely a consideration. And then sometimes in these central systems, it's a good idea to include some sort of preconditioning that's going to help with, you know, we talked about that those design temps, you know, in the very coldest hour of the winter, trying to stay above 62 degrees, you know, that air that's being supplied to the spaces trying to keep that above. So with the central system, with sort of a single piece of ductwork, you can maybe add a whole coil, right? Like a separate kind of heat pump that is going to be able to precondition that air. It's also going to aid in dehumidification during the summer. So we see that pretty commonly in these designs. So here is a central system layout in an apartment unit, a single apartment unit. So again, for passive house, exhausting 25 CFM out of the kitchen, exhausting 20 CFM out of a bathroom, and then supplying that same amount to the living spaces. So 15 CFM is going to come into this bedroom, 15 CFM is going to come into the other bedroom, and 15 CFM is going to come into the living room. All of it is being tied back to a central riser that is either supply riser or exhaust riser, and that's traveling vertically up and down the building. So you need to make room for, you know, that amount of that ductwork, right? Whereas before with the unitized system, sort of all this ductwork is up in the ceiling. You know, you might have a closet, but you might just be able to have the ERV up in the ceiling as well. So doesn't take up necessarily square footage of floor area in a central system. You need to make provisions for the risers. What about duct sealing? So duct sealing on any kind of ventilation system, any kind of ductwork, whether it's heating, cooling, ventilation, whatever, is a priority for the high performance projects. The reason we talk about it sort of ad nauseum with the central systems is that, actually, yeah, this should say central system. This is a central one, not individual. Anywho, because there's so much of it, and because it's spread out over such a large area, paying attention to it and trying to visually see where all of it is sealed and everything can be very difficult. A lot of times on our projects, on Stephen Winter projects, we are talking about AeroSeal to seal the ducts from the inside out. We're talking about that with the design team, the owner, to sort of budget that into the process. Just because there is so much ductwork spread out across such a large area, we have found that, you know, using the AeroSeal technology is a great use of the technology for these ventilation risers and branches, you know, everything of the system to do that AeroSeal. And we say required because we're kind of like saying, no, on these larger projects that do a central system, it is kind of a requirement. It's kind of, now I don't want to say the only way to meet the requirement, but it's a pretty cost effective and saves everybody a whole lot of headaches, and just takes one thing that could go wrong, you know, sort of out of the equation in terms of getting passive house done correctly in the field. Okay, so you might say, well, Scott, thanks for the recommendation, but what's this actually look like, you know, in the real world? And so we did a little mock-up testing. This is sort of a little mock-up of you know, simulating a ventilation riser. We've got some branch ducting here and some boots simulating, you know, supply and exhaust registers, right? And so you can see it's unsealed right here. We're actually testing the ductwork to see how tight it is. And so these are the results of that unsealed, just you know, pretty rough. There's not a lot of tape or anything on here. You know, it's not all that well done, but you know, these types of gaps and cracks, you know, we see these on real project sites all the time on the ductwork. Anyway, the measurement was 45 CFM, almost 46 CFM of leakage on the ductwork. You can see we pressurized it to almost 50 pascals. For the central systems, that's how we test the ductwork, at a 50 pascal pressure difference. Sometimes they're operating at a higher static pressure. And I realized, for a residential system, for a unitized one, we would probably test this at 25 pascals of pressure, sort of more equivalent to an industry standard. Anyway, so takeaway here, 46 CFM of leakage. Here's what sealing it might look like. And so this is a painted on mastic. Mike's sort of going to work on these, the traverse joint, right? The long joint along the back. This was installed up against that CMU wall sort of on purpose, right? A lot of times there's not much room within these ventilation risers to get the mastic on, and that's kind of what we wanted to simulate in this mock-up. So painting it on is really what the manufacturer's directions, direct you to do. We typically tell guys we want to see that thickness be at about a nickel's width, right? The thickness of a nickel is what we're looking for. You can see he's going to move to the upper parts of it. And as he works around all of that other, stuff that's in the way, it gets a little more difficult. So trying to have this ductwork not pinned up against stuff is another design consideration. It's a difficult one to accomplish, again, because of space constraints, but it's something to consider. So he's really laying it on thick. Yep. All right. So nice job, Mike. Looks like he sealed it up about as good as you can. Now, how did this test? Here we've got our duct pressurization fan hooked up again. This is a small theatrical fogger that we use to fog the ducts so that you can see, the fog is being pumped in through the fan into the ductwork. And so you can see we've got some puffs of fog happening up here. I think there is also some that is falling down from below, but really the most obvious one right here is around this short seam that, we can't get to the back side of it. And guess what? It's leaking. It's leaking, quite a bit. And oh yeah, up here as well, we've got some other leaks developing all around, I don't know if that's around, it might be along sort of, there's a longitudinal seam here too, that if you can't get back there, it's going to leak. And I think that's what's happening. So anyway, Mike did his best to sort of seal this thing as good as he can, and you can see it's leaking quite a bit. Here is sort of close up of what's going on. So that's that seam that we could not get to because it's up against the CMU wall, really leaking quite a bit. Any other areas that just could not really get to? Yeah, kind of out of the top of it, because at the top, as it's against the wall, you can't get to it and it's going to leak. So either keeping it away or figuring out a better way to do this in the field to get everything sealed up is needed, especially in passive house. If you have leaky ventilation ductwork, it's not gonna you're not gonna get the flow rates that you need from the registers, and you can't just turn up the just the supply side of the system, right? Like it's in an ERV cabinet. So the amount of control that you have and the ability to sort of balance it is impeded. You're restricted by how much you can just turn the fan up. both for the energy model and for getting a balanced flow rate, which is why we talk so much about leakage. So you can see this one was reduced down to 23 CFM after sealing the accessible seams, but minus the back seam. 23 CFM for a system that is super, super small, still not very good. That's pretty leaky and probably would not pass. So here's what this is going to look like in the real world. So this is, you know, a large building with large risers going up and down. You can see that that hole is just, you know, leaking like a sieve. It's very difficult to spot that hole without having fogged it. It's difficult to spot it even with fog, but you know, spotting that without fog is impossible, especially when you are looking at a building, you know, that could be 12 stories tall and this ductwork spread out all over the place. So you might be asking, how can we not have all this leakage? Well, AeroSeal is a really good option. Duct sealing from the inside. During our enclosure air sealing stuff, we talked about AeroBarrier. This is the same parent company. I'm not sure if the actual sealant is the same or not. It's very close. It's a water-based sealant. But this AeroSeal for duct sealing was sort of the first, you know, this came before AeroBarrier, before the, you know, the whole building leakiness mitigation thing. This is for just duct sealing. And so there's a machine that sits up usually on the roof, right? Like this is usually done from the roof into central system risers, but it can also be done on, you know, small, you know, any kind of ductwork. And so no need to manually locate the leakage. It can seal up to holes up to about 1/2 inch. And so you can see here, this is definitely on the high end of a 1/2 inch hole in the ductwork. And this is before and after applying the AeroSeal product from the inside. You know, that hole has been filled with the sealant, with the aerosolized sealant. There's a video of it really being applied. This is the mist being, you know, fog being added. And then this is controlled with the computer. I think there's actually two risers being done there at the same time. So again, pressurization fan, the air moves through. This is where that sealant and, you know, aerosolized sealant is pushed in. So in terms of design and getting this into your project, they've got specs, trying to get it in early, ensure that all components of the duct system are installed so that all areas receive the sealant. Got another slide that talks a little bit more about what we mean by that. And you can see the amount, the leakiness that we're talking about here. So supply ducts, return ducts are going to have air losses of less than 3% of the total airflow of the volume measured at the fan or air moving device. So, you know, you have a central system that is going to do, let's say it's rated to move 1,000 CFM of air, times 0.03, 3% of that. So 30 CFM of leakage is what 3% would represent if you have a system that's moving 1,000 CFM. So very, very tight ductwork. And we're saying this is what you need in order to hit these passive house targets in terms of airflow being delivered to the space, exhausted from the space, and then also the total amount in and total amount out. through the ERV itself. What are some other system components that you want to think about when doing this design and install? Well, we want the ventilation system to be quiet. This is more of a PHI, Passive House International, Passive House Institute. They have sound limits for supply air to the rooms and rooms in non-residential buildings, right? So it can be a little louder in those areas, but where somebody is living, there's a 25 decibel sound limit. High quality filters, so MERV 13 or MERV 14. Again, this F7 is a European rating system, I believe. You want to have duct insulation for intake and exhaust ducts that have a vapor tight seal. We'll see those in a second, an R8, but that's this, right? These ducts are going to be cold. They need to be insulated. They're going to be cold in the winter. They're going to be cold in the summer. One duct is going to be cold in the winter. One duct is going to be cold in the summer. That's why we insulate both of them. And with that vapor tightness, thoroughly sealing it, and then a way to actually balance this, the ductwork, right? Balance the flows. So how have we balanced, how have we seen that done by project teams? Usually a car damper, this constant airflow regulator kind of damper. And you can get them in certain, they're sized to the flow rate that you want to see out of your system. They come to the project site pretty much pre-balanced. Usually there's some fine-tuning adjustments that need to be made for Passive House. This is what that damper looks like as it's actually operating. You can see that that blade is sometimes adjusting to slight differences in the static pressure. So as the static pressure goes up, it closes a little bit more. As the pressure goes down, it opens a little bit more. All in an attempt to maintain that constant air. Yep. Yeah, so constant airflow regulator, a great thing to consider in the design. Other stuff to consider. Another Passive House requirement for the kitchen ventilation, sort of the kitchen exhaust register. If you do exhaust air out of the kitchen, the ERV needs to have a minimum of MERV 13 for the rate for the filter. MERV 13 is kind of what you want to have regardless. In addition to that, you need to have a MERV 3 filter on the kitchen register itself. So this usually is like a washable mesh. This blue filter product we've seen is kind of like the least expensive. It meets the MERV 3 requirement. It is washable, but it is cheap enough that, if it does get gunked up, or not if, when it gets gunked up with grease, that it can be changed. And it's another added protection to the ERV itself, right? Spending a lot of money on that ventilator, you want to protect it. The kitchen grill has to be a 6-foot minimum distance from the stove. And so because this is being used as sort of the exhaust system for the range in a Passive House design, right? You'll also have a recirculating range hood over that cooktop, but this register in the kitchen wants to be within 6 feet of that range, so that it actually, is going to do some kind of air change in the kitchen itself, which, as we talked about last time, is one of those rooms that you want to get that bad air out, and you want to get it out quickly. So in passive construction, it's usually with an ERV port, an ERV return register in the kitchen, located at least 6 feet from the stove, with the washable filter. What about the outside ports, right? So we talked about the interior registers. So on an ERV, on a balanced system, you've also got outside ports. So the consideration here is you're probably going to have to clean these from time to time, the intake port at least. We've seen them get kind of gunked up. It depends on what kind of, what the register on the outside actually looks like and does. At a minimum, it needs to have some rodent screen to keep any pests out. But aside from that, also keeping them protected from snow, right? So if your port is on the roof, either your intake or exhaust, you want to make sure that that is probably at least 2 feet above the roof deck. So this is a rooftop ERV. You can see it's up on some dunnage here. And I think these are actually solar panels that are on top of it. This is it's a solar racking system, right? For rooftop solar, but yeah, you want to keep these intakes and exhausts free of any blockage. You also don't want to have any intake from, like the exhaust, right? They need to be, in Passive House world, it's 10 feet apart. I think that aligns with mechanical code as well. So, you don't want to be pulling the air that was just exhausted from the neighbor's apartment. You don't want to be pulling that into your apartment, right? You want to keep those ports separate. All right, so we are coming to our 5-minute break. If there are any questions, please let me know. Otherwise, we're doing pretty good on time. We can take a little bit longer break. And Jamie, anything in the chat?
Just a clarification on the grill for the range. Was it at least 6 feet away from the range or within 6 feet of the range?
Within 6 feet. I think it's within 6 feet. It's a poorly worded requirement out of FIAS. If you, sorry for anybody from FIAS on the line, but I believe the intention is that you want to have it be within
minimum distance. Okay.
I can look at that during the break to make sure
okay.
Make sure.
Another question that came in was about integrating ERVs when you have ductless heat pumps and how that can work. And maybe you'll touch on that a little bit later.
We won't. We talked about integration during the last talk, not with ductless. Talked about with ducted heating and cooling. And yeah, I mean, at that point, if you have a ductless heat pump, you're probably just going to run, your ventilation supply and exhaust, separately. It's an independent system at that point.
Basically, just a separate system of ductwork just for the air.
Yeah. And to be honest, it brings up a good point too, that even when you have ducted, heated, and cooled ductwork, like you have a ducted heat pump, to meet FIAS, you're going to need to separately duct your ventilation system.
Oh, yeah.
There's just no other way around it. They want to see a minimum of 25 CFM out of the kitchen, 20 CFM out of the bathrooms, and they want that ventilation air to be provided directly to the living spaces 24/7. And so that usually means a separate system.
That's actually really good to clarify, especially since we're talking about the duct sealing and how important that is. That means that you're going to have to seal 2 different sets of ducts potentially. So.
Yeah. Usually, we see more problems hitting the flow rate requirements out of the ventilation system than we do the heating and cooling system. Usually there's a lot more capacity, and that heating, that fan is much bigger, and the tolerances are much bigger, right? Like it's not as, we're not as fussy about that. The ranges are bigger, but with the ventilation systems, the tolerances are much smaller. The fan flow rates are smaller. It's just a lot more accuracy needed.
Okay. And then real quick, just before the break, somebody was asking for duct sealing. We talked about the mastic and the aero seal. Can you use foil tape? Is that acceptable?
If you are really good at using, there's a mastic UL tape. It has a mastic to it. You could use that. I've seen that used, and if the installer is skilled at that, yes, you could use it.
So like an aluminum tape, I think is what they're asking for.
Yeah, just a straight up aluminum tape. No, you're probably not going to get to the levels of sealing that you're looking for. That
Perfect.
mastic totally needs to, come along.
Awesome. All right. Well, let's take a 5 or 6 minute break and come back in a little.
Cool. Yeah, we'll be back at we'll say 3:06.
Sounds good. Thanks, everybody.
All right. So I was able to clarify, Jamie, that ERV exhaust port in the kitchen wants to be at least 6 feet away from the range.
Okay, so you have like a 6 feet radius from the range. You want to make sure that's outside that.
You want to make sure it's outside that. Yep.
Perfect. Thank you for clarifying.
Thanks for somebody, whoever asked that. Appreciate it. All right, let's play some What's Wrong with This Photo. We're going to fire up the poll again. This one's a nice warm up. We had this as one that was part of our air sealing. What's wrong with this photo image as well? So we've got an opportunity for y'all to tell me what you think is wrong with it by using the poll. Here's the photo again. We've got what it looks like in plan, what they actually gave us in the build. Anybody wants to chime in? We'll have a little fun. We've got some other images to critique as well. The next one's going to look like this, another easy one. But I'm wondering if you all can tell me what's wrong with this image using the poll. All right, well, nobody wants to participate. You're just going to have to listen to me drone on about it. What's wrong with this is that the vapor barrier is not sealed to the air barrier of the wall. And that's going to be a problem because during the winter, when it's really cold air moving through this duct, there's a metal duct underneath this, water is going to condense on that duct and it's going to just drip right through. It's going to get all of this fiberglass insulation nice and wet, and it's going to be a big old problem. So got to get that air barrier tied into the vapor barrier of these ductworks. Yeah, air leaks. I mean, there's probably air leaks, here, right? This is probably, the duct itself is probably not sealed as it goes through the wall, through the air barrier of the building. But really, more importantly, the vapor barrier needs to be sealed. You cannot see that fibrous insulation on these ERV ductworks between the outside port and the actual ventilator. All right, how about this one? This is an easy one. What's wrong with this image? Got some riser ductwork here. There's some telltale clues in the picture about what is wrong with it. Yeah, the portion is not sealed. That's up against the wall. It's not sealed. It's not sealed because there's mastic all over the wall. So as this thing was laid in there, it's too close to the wall. As they painted the mastic onto the joint, they tried to get around it as best they can and left all that mastic on there. This is higher up in the ductwork. It's not sealed or against it. Yep, nice. How about this one? What's wrong with this thing? I don't think you need a clue, but the clue is we're up on a roof when we're taking a picture of this thing. Yeah, it's dirty. Like one of the dirtiest filters I think I've ever seen. This is a very big filter too, right? Like you can see the width over here. Dirty, unchanged filter, right? And so what's going to happen? I just had this happen last week, well, 2 weeks ago at this point, but had an HVAC contractor do their own balancing on a rooftop ventilator. They went down, there was only 10 apartments in the building, so small apartment, small building, but all the flow rates, they said they reported flow rates. I came back you know, within 3-4 weeks of them doing their own testing, and found, you know, a lot of apartments, a lot of registers were not meeting the minimum requirements for flow rates. And it turns out, you know, even though the HVAC contractor left behind filters for, you know, for somebody else to change, they told them like, these need to be changed. And of course they were not changed. And so it was causing us to have much lower flow rates on the exhaust ports. So the filters need to be changed. This one might be a little tricky. Way to see that's wrong with this image. This is a constant airflow regulator. And I think well, I showed you a picture of what it looks like, what it usually looks like. Wondering if anybody knows or can spot what is now on this thing. Good guesses. The damper is stuck open, and there is, it's not corrosion. This is actually AeroSeal product. So hot tip, you know, if you are going to use AeroSeal on your central ductwork or any kind of ductwork, you want to make sure that the dampers, this is a car damper, that they need to be removed. Otherwise, the AeroSeal is just going to gum them all up. So this was a damper that was left in the ductwork while AeroSeal was being installed. And it's now no longer constant airflow, right? It's just sort of permanently in that same spot, which is not how the car damper works. It wants to adjust to the amount of static pressure that it is seeing. And so it can also just completely fill around the damper opening that AeroSeal product. So yeah, there you go, car's wrapped. All right, this one I don't think you're gonna get, so I'm gonna tell you what's wrong with it. Although if somebody wants to try, go for it. For image 5, this is again ventilation ductwork on a central system. AeroSeal is being slated to be installed. The big hint here is that the kitchen is way over here. This is the bathroom. You know, the bathroom is also located way over here. So what the installer has done is put in, they didn't put in like the very last bit of ductwork to get to the register. Like there's 10 feet of ductwork that's missing. And so trying to do that AeroSeal, the angles. Oh yeah, good one. A little bit of jogging around here. So it comes down and then it's underneath. I think this is all designed because this is either supply and then this one is exhaust, and it's sort of like, you know, origamiing around there. I think that's all been designed. Same thing here though, but that, I can see your point. That's a good catch. The answer though that we're looking for is they did not complete the installation. They don't have all the ductwork there that needs to be sealed before they're going to start AeroSeal. What about this? What's wrong with this image? So again, this is a register boot. This looks like an exhaust boot. So it looks like the grill. Well, the grill, you know, you can see a grill was installed. We took it off for the photo, but you might see what's wrong. It's kind of within this, in the same vein of the last one. Yeah, the connection is not sealed. So imagine putting the grill register now on top of this drywall. There's a big gap here. Like this is kind of, you know, this piece of ductwork wants to act like ductwork. If you've got a space between there, what we're gonna try to measure here at the register with our flow device is going to be impacted by the amount of air that is getting sucked in through this gap. and not being picked up by our flow measuring device. And so what you need to do is seal the drywall, in this case, tight to the register, not the register, tight to the boot, tight to the boot. Yep, not sealed to the drywall, right on. This one is also very hard to tell what's going on. Basically the insulation that's on this ductwork has just completely fallen apart. It's completely coming off. Really pretty shoddy workmanship, but you know, this is going to turn into a condensation nightmare again. This ductwork, this fibrous duct insulation needs to be in contact with the actual metal ductwork in order to work. All right, we're gonna move on to testing, adjusting, and balancing. Got about 20 more slides, so plenty of time to get through the rest of this material. TAB stands for test, adjust, and balance. We talked about a lot of those ventilation tolerances within passive houses being very tight, and that total supply and exhaust also need to be within 10% of each other in terms of being balanced, and they have to meet 100% of the design flow. So I hope that you're starting to get can visualize, you know, what we're up against when we do have a lot of leaky ductwork for ventilation. In a passive house project, you are limited to the amount of fresh air and exhaust air that you can push in and pull out. They need to be within 10%. You can't drop below the design value. So, you know, in a typical job, like, you know, you have the ability to sort of turn up the ventilator, turn up your fan, you know, have more flow. We're really hampered by how much we can do that in a passive house job. In FIAS, the minimums on the exhaust side have to be met. You're not going to get certified if they're not. If you have a picture of a kitchen exhaust port pulling, you know, 24 CFM, probably not going to get certified. It's not meeting that 25 CFM. You've got to be able to demonstrate that it met that. Same thing for the bathrooms, 20 CFM out of there for exhaust. With the supply rates on each of the registers, each of the boots, there's a little more wiggle room there. But on the whole, again, you've got to be within that 10%. So once you get all of your exhaust flows to meet the minimums, now the supply flows are sort of locked in, right? There's no wiggle room there. They have to be within 10% of what is being exhausted. And the exhaust has very hard minimums in terms of, you know, set minimums that you have to meet. So it's kind of like a perfect install. It's kind of what FIAS is demanding on these ventilation systems. You can make airflow measurements on these on the ERVs. You can do that with a traverse. You can do that, you know, like within the ductwork. There's a product out there called a Keeley FXP measurement port, and that's what a lot of raters. That's how I was trained as a rater to make these to make some of these measurements. So it's an in-duct measurement, sort of like right at the ERV itself. It's helpful. You can also make that measurement, you know, at the port that is like outside, right? Like the outside intake and the outside exhaust. You could also make that measurement of trying to say whether the total supply and total exhaust are within 10% of each other.
Scott, real quick, can you explain again that 10% and the reasoning behind that? Somebody's asking for clarification.
Yeah. Yep. Let me see. Yeah, let me go back. We have plenty of time here. I'm just going to go back to a diagram is going to be a lot easier to explain this. And I'm glad that you asked, because it is kind of like besides blower door testing, like this is the next hardest, the next thing to really master and do well. And I think I want to use, yeah, one of these very first ones. Okay. So there's 25 CFM in this plan. There's 25 CFM being exhausted out of the bathroom, 25 CFM being exhausted out of the kitchen. There's then 25 CFM being supplied to, this is the living room, and 25 CFM being supplied to the bedroom. So what we're saying here is that not only do you need to measure what the flow rate is at each of these registers, right? There's 4 registers. You also need to measure what is the total incoming and total outgoing to the living space itself. What is that measurement either at the outside port, at the outside louver, or what I was just saying is sometimes we prefer to make the measurement in the duct itself. But the duct that you would make that measurement in would be the one that is connected from the outside port to the box, and from the inside, from the outside air to the box, right? Like you need to make 2 different measurements there. So altogether, to get this thing in compliance with BIS, demonstrate that it is in compliance, we're making essentially 6 airflow measurements, 1 in each of the boots, and then 1 at each of the intake and exhaust, the total intake and exhaust for the apartment. And what I was explaining about the 10% thing is that the 10% is taken on the total. So this louver A and louver A, these need to be within 10% of each other. It can be, it's plus or minus 10%, but not really, because the exhaust flow rates here, you need to meet these minimums. You can't be below 25 CFM as you measure these ports. And so let's say, just follow this logic out with me. Let's say you measure 20 CFM in the bathroom. So you're 5 CFM short of, for this design, what you would need. Or let's say you measure 20 CFM in the kitchen, right? You're 5 CFM short of what you need. So the options are, okay, let's damper this thing down a little, or let's open this damper up, damper this one down, and try to get it to be a little more balanced. Sometimes that works, but what if you wanted to try to turn up, how fast this ERV is actually spinning? You can do that, but then you've also got to make adjustments to the supply, right? Because the intake and exhaust on the whole need to be within that 10%. And so it really kind of like you get painted into a corner in terms of making these adjustments. There's only so much adjusting that you can do. And the reason that we're doing these adjustments is usually to account for or accommodate duct leakage within the system, right? And so it just becomes a little tedious to actually get this to work in the real world with these airflow rates. I hope that answered the question a little bit better. I'm gonna go back to, okay, I'm gonna go back to where we were. And we're going to talk more about balancing now. Yep, that's where we were. Okay, so the 10% wattage. Also, we need to measure the wattage of the ERV, how much electrical draw it's using. And this is another reason why you can't just, infinitely turn up the fan on the ERV. As you add more, usually as you spin those fans faster, a lot of times, the wattage that is drawn in terms of CFM, in terms of watts per CFM, we've got to hit that efficiency number as well. A lot of times in an ERV, as you turn up the amount of CFM that you're asking the fan to deliver, the wattage increases unproportionally to the amount of flow rate that you're looking for, i.e. fan now has to work harder to supply more flow, and so your efficiency metric drops. And that's why we talked about trying to size those ERVs, giving yourself some room so that the typical 24/7 operation is sort of within that like 50 to 75% of the operating capacity of the fan itself, so that you've got some wiggle room there. So tab requirements for FIAS also, this is getting a little more nitty gritty, but if there's going to be a third party, they need to be certified, a certified air balancing professional. And we are recommending that we do a pre-meeting with the tab contractor to discuss what the expectations are. Because the tab and the scope of work for that tab contractor is usually something that is way different. It's way more involved than what they're used to doing. And depending on the type of the design, like it is like way more than what they're used to doing. So getting their scope of work correct, a lot of times we'll like review a scope of work just to make sure that everything is, you know, that they've bid everything, and that the owner and the contractor, you know, the general contractor is buying what they need from the balancer. So single family home, single ERV balancing can be done by the equipment manufacturer. So in the case of that Zehnder, you know, that manifold system, part of the cost, as at least it used to be, and I think they still sell it this way, part of the cost of the product includes having one of their reps come out and balance your system. And FIAS will accept that balancing report from the manufacturer in that case. For larger, more complex systems, that communication, the planning ahead, like I said, we'll sometimes review the submittal from the tab contractor, and being sure that those specifications state that the balancer is going to work with the manufacturer's rep. If it's a larger system, there's going to be controls that are involved, that they're going to work with them. And then a bullet just to remind, you know, most times the tab contractor is a subcontractor of the HVAC contractor. And so there can be some interesting, you know, interactions there. So before the tab contractor is going to start anything, this is generally what we're seeing, what we are asking of them. We want to see what the intended procedures are. We're asking them for a blank project-specific report, like, you know, what does your report look like before you start inputting any of the results that you got? We want to see a marked up drawings, so it's sort of a tab plan, like this is now the tab contractor saying, I am going to, you know, measure the following areas, like all these registers are what I'm going to make measurements on. And so within FIAS, because there's sort of so much more balancing required than what is typical, this is a really helpful point. And then before any site work begins, I've been doing kickoff meetings with the tab contractor, separate kickoff meetings. So it's also really helpful to be on site the same day that the tab work begins, just to make sure that it's all, you know, starting well and going well. But yeah, the kickoff meeting has been really helpful for my projects because you know, we would have done like maybe a construction kickoff for the GC and you know, maybe like the framer and the drywaller talking about airtightness of the building envelope like months before. But tab work is done, you know, as the building is like finishing, right? It's one of the last things to happen before people move in. And so having another kickoff meeting with the person who is actually going to be making the measurements on site has been pretty helpful for the projects I've worked on. Here are some third-party balancing professional certificates. NEB, AABC, and TAB are a couple of them. Like I said, having a pre-meeting has worked well for my projects. The unitized ERVs, developing a strategy that's going to allow, wait, what are we trying to say here? Access strategy must be developed in ERV closest to access. Okay, so how are we going to, like in a bigger building, how are we going to like actually make the measurement of that total flow in and total flow out? And this is where sometimes we're going to be doing that in-duct measurement. So like if you have a taller building or even on a single family home, like can you get to those outdoor intakes and exhausts to make the measurements? If you can't, we need to have a provision or, you know, figure out a way to do that and figure out a way to do it together so we don't mess up each other's work. Yeah, I think we've talked about this. So the instruments, the stuff that you actually use to make the measurement. Our preferred method is to use a powered flow hood. This is what a powered flow hood looks like, at least, you know, one example of that. To our knowledge, it's the most accurate piece of equipment to measure airflows and low flow airflows at that, right? So under 300 CFM is considered kind of like a low flow. And so there's this LBNL report that sort of found that there's a wide range of reported accuracies within some of the equipment that is available out there. And the long and the short of it is to say that an active flow hood, i.e. a powered flow hood, has the lowest margin of error at 2%. Some of the stuff that's available out there can have, you know, 10, 20, 30% range. And so that's not going to really work for these passive house projects, because if you have your tab contractor using a, like a, let's say it's a commercial hood that is capable, only capable of measuring a flow rate that is at or above 100 CFM, and the register that we're trying to measure, you know, we're targeting 25 CFM, like they're going to go around and make the measurement with their large piece of equipment. It's going to give them an inaccurate number, and then they're going to make balancing decisions based on that inaccurate number. And then we as the FIAS rater are coming around to sort of like spot check and spot verify these flow rates in a sampling of apartments. Well, I mean, we always find that those flow rates are not, they're not accurate. They don't match the report that we were given from the tab contractor, usually because their piece of equipment isn't even capable of measuring those low flow rates. So the whole reason for the slide here is to say that in FIAS world, we need to follow this ANSI ResNet ICC 380 standard for measuring airflows. And this powered flow hood is the best option that we see that's going to be able to measure both supply and exhaust rates and be in compliance with this ANSI standard. A little more information about CARS and where to place them, these constant airflow regulators. What we want to see, well, what we do see is, even though they come from the factory sort of preset, there's often a small amount of balancing that actually needs to happen on site, you know, with the car damper actually installed, right? And it's usually from a screw, like somebody needs to be able to get a screwdriver in there to either slightly open or slightly close how much that bladder is going to move. And so what we're saying here is make sure that if you're using a car damper, that somebody can actually make that measurement. Place it somewhere in the ductwork that somebody can take the face register off, stick their hand in there, make the adjustment with the screwdriver, and then put the register back on. It can't be so far down in the ductwork that you can't get to it. You don't want to be having to cut into ductwork to make this small damper adjustment if you are going to use a car damper. Which is what all of this says. Don't use it after, don't put it in there until after aeroseal.
Scott, quick question.
Mm-hmm.
For the car dampers and other kinds of adjustable dampers, like if you have a tenant in your house here, like for example, and somebody was asking, could a tenant or a user mess with that flow after it's installed?
Yeah, there's no rule that the thing that you're using to damper the air needs to be, indestructible or not, messable by the actual tenant. The car dampers have that added sort of advantage of being behind the register. But there's a lot of stuff out there that's available, opposable blade dampers where the actual register is the damper. And that they're allowed by FIAS. We sometimes, it can get a little noisy when you're using the actual register to damper down, especially when you need to like really damper down a flow rate. Can get a little noisy, but car dampers, if you really ratchet them down, can also be noisy. So another kind of pro and con, but the answer to the question is yes, you can use the register to make these dampering adjustments, and it can be accessible to the tenant or homeowner or whoever. The requirement for FIAS is to show, at the time that the rater was there, can we document that these flow rates and wattages and everything were achieved? And that's the threshold for being compliant or not.
So in other words, it's probably a good idea to get it checked every year or two when you get your normal HVAC services and stuff.
Well, yeah, I mean, unfortunately, a lot of HVAC contractors, they do not own a flow hood. Or if they do, it's not capable of measuring these relatively low flow rates. You see it job after job after job. And, those are the guys that are doing the new construction. If your service tech is coming out, they are not going to have that piece of equipment to make those measurements. So that's why we talk about these, the filter changes, like what is going to really slow down your airflow? Well, it's a dirty filter and it's a dirty intake from the fresh air are usually the two biggest culprits. And that should be something that, your service professional is gonna take care of. Other stuff about central systems, the fancy passive house equipment has readings from the actual equipment. You can look at it either in the onboard display. Sometimes you can plug in a computer and also check it, but usually there's an onboard display, and you can see what the fan power is. You can see what that consumption is for the exhaust fan, the supply fan, etc. And that is all very helpful information, not only in certification, but also in if there's any troubleshooting that needs to happen for those airflows. Not on the unitized ones, though. You're not going to get that. This is on these pretty fancy rooftop ones. So what does this look like for measuring? Oh, good. Look, here's this inflow measurement, right? That is a Keeley probe. I'm making the measurement between the ERV itself and the outside port to say, what is the pressure difference? So you take this number and translate it into CFM. It's actually pretty reliable, pretty accurate way to do it. And then for the same system, I'm also recording what is the wattage, right? Like this is the plug to the ERV. What's the wattage of that? And then sometimes if it's not a plug-in type of ERV, you're going to have to get more sophisticated with a power meter and another way to measure how much wattage the actual ERV is drawing. So a power meter might be needed. More about tab reports. This is a typical tab report. So you can see the outlet number, the size of everything, what type of what type of register usually, right? And then this is the good part, right? This is what design CFM flow was. You can see these are all very low. This is for an ERV. These are all of the different ports that are connected to the ERV, and magically, all of the measurements that they made are precisely exactly spot on. There's no deviation whatsoever. They are all meeting that actual, design flow rate. And so I hope you're picking up on the sarcasm in my voice, because let me tell you, I've been measuring airflows for a long time now, and you will never, ever get this amount of cooperation between what was designed and what you actually measure. And so when we see reports that come from tab contractors that look like this, it is an immediate red flag that they did not measure those flow rates, or worse, or something else, right? So more tab reports, and so it doesn't come through here all that great, but yeah, a perfect balancing report, design and actual, right? So in this particular setup, there was actual speed controller that was available to the balancing contractor. When we went back through to sort of verify these flow rates, we could see that none of the actual speeds of the ERV were changed. They were all just at the factory default setting, and so no adjustment was made by the balancing contractor. They're just now, they're reporting that everything is fine. When we tested this particular system, it wasn't. That it hadn't been balanced at all. And then timing, it usually is going to take several rounds to get the balancing correct. The test and adjust the balance of these ventilation systems is the last major item that is needed before tenant move-ins. Unfortunately, it's also the last major item that your FIAS verifier also needs to get right. And the FIAS verifier is subject to quality assurance by FIAS themselves. And so, they and me, like, we are not going to be trying to pull any wool over anybody's eyes, right? We need to have photos of what it is. We need to, document that this system is in compliance. And so when a project team sort of like finishes their whole building blower door test, like, it's not like you're at the end. It's not like you have a certified building. You now have to go on and focus on the ventilation balancing, because it can be a big deal. It takes a long time, and often many, many rounds and iterations of measurements and whatnot. Here's some resources. This will be in the slide deck that we send around, but some other standards and areas to go for more information about balancing. And then these are sort of my final slide here about project success for construction. Ductwork shop drawings are very helpful. This is, the HVAC contractor saying, okay, this is how I'm going to install this ductwork in this building. You're going to want to see that probably as the FIAS verifier, just to make sure everything is still okay. Mechanical engineer should be engaged during construction and also conducting inspections. You can never have too many eyes on these systems. Talked about early engagement of the tab contractor. If you are going to use AeroSeal, get them involved early. You don't want to wait and keep them in your back pocket and say, oh, we'll see if we pass, whatever pre-testing you're going to do. That's going to push the time frame back, and it's not going to work out. You want to have, if there's any inkling that you're going to need AeroSeal, get them involved, during pre-construction. Talked about contractor trainings, aka kickoff meetings, stuff to do, and then be on site when the tab contractor is beginning work, so that they're crystal clear on what we're looking for, what the expectations are. So with that, that's all I got. If anybody wants to give me any more feedback, let us know what you think about final takeaways. Please do so in the poll, but you can also.
Can we go back to the additional info page you just had up?
This one?
It might have been the one before. That one, I believe. Somebody was asking for that. Thank you.
Mm-hmm. Yeah, so that's all we got. That's everything I know about Passive House, I guess. This being the end of the third workshop. We've done this in 6 parts, so thanks everybody that has listened. I hope you found it helpful. Got a few more minutes if there are any more questions, but otherwise, thanks.
The only unanswered one that we have so far was about somebody asked if you need to take the ductwork apart to get the dampers back in after AeroSeal, which then defeats some of the sealing.
Yeah, so usually we see the damper, the car damper, between like the register boot and the ductwork. So at like the very end of the run. And a lot of times AeroSeal is happening before drywall is in. And so you're able to make that final connection.
Great. Well, if anybody else has any other questions, please chime in now. And Anna, do you want to talk about the survey real quick while we're waiting for other questions?
Yes. Yep. So I'll be sending out some surveys. One is for general feedback. Another one is if anyone in the audience wants to receive AIA or BPI CEUs. That'll be a second survey, so look out for that. And just as an FYI, you had to have attended both parts, part 1 and part 2 of this workshop to get the CEUs. And so yeah, I'll be sending that out in a couple days along with a link to the recording and PDF slide deck. That's it from me.
Great, yeah. The only things that are coming in now are just a bunch of people saying thank you. So nice job, Scott. And yeah,
Great.
Seeing you again in the future for some more awesome workshops.
That'd be great. Thanks, everybody. Have a good day.
Okay.
See ya.
Thank you.
All right. Thanks, everybody.
Bye.
Bye-bye.